Hello, gremlins, monsters, ghosts, creeps, and whoever else happens to be watching, maybe my students. And let's go ahead and get started on the homework helper for section 2.6. My name is Victor. Hello. All right, so let's go ahead and get started. The very first section, we're talking about looking at exponentials in different formats. We have it in exponential form where it's listed as a base number with an exponent. And a base number with an exponent means it's that base number multiplied by itself, whatever that exponent number of times is. So in this case, it would be 5 times 5 times 5. And so then what it's asking us to do is it wants us to look at these other forms and work backwards and forwards to see what we can do to get it into the form that we need. So let's go ahead and look at these just for a second here. Sweet. All right. So when we see that we have 7, 1, 2, 3, 4, 5, 6, 7 times, that means our base is 7 because this is a 7, but we're raising it to the 7th power because we have 1, 2, 3, 4, 5, 6, 7 of them. And then to find the standard form, I'm going to zoom in a little bit, we can do that in our calculators by hitting 7 caret 7. Okay? Let me do that one more time for you guys. So I hit, well, let's get this on screen even. Maybe without the glare. Oh my gosh. Technical difficulties over here. So I'm hitting the 7 right here. Hi. 7. This button here is the caret button. Caret 7. Except I shouldn't hit 77. 7 caret 7. And that tells us it's this very large number, 823,543. All right, let's do it the other way. So we got 2 to the 10 power. So that means I need to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I had to do 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do 10, or 2 to the 10 power. Now I just do 2 caret 10, and I get 1,024. Beautiful. All right, let's do it again. So now we have 81. It's kind of tough when we're given a number over here. We have to kind of work backwards to figure out what it could be. So whenever we have that and we're trying to figure it out, essentially what we're doing is we're factoring, okay? So what we're actually doing here is we're trying to factor 81. So what we want to do is we want to look at what multiplies to be 81. So 81. Well, I know 81 is 9 times 9. I know that. So this could be 9 squared. But I bet we could get 9 broken down as well, because I know that 9 is 3 times 3. And so that 9 is also 3 times 3. So it's also 3 to the 4th power. So this is the most basic version. This is the one with the smallest base, with a prime number as the base. So we can do that as well. So now that we know that, I know that this is 3 to the 4th, so that's 3 times 3 times 3 times 3, etc. And I think you guys get what this one's asking you to do. So let's go ahead and go to the next section. So for this next one, it wants us to provide at least 3 equivalent forms. So what it wants us to do is it wants us to play with it in some way such that we are either multiplying bases so that their exponents add up, or we're raising the powers so that those exponents multiply. It wants us to use a couple different rules. So I definitely want you guys, as much as possible, to do as many different forms as possible. So when I'm looking at this first equivalent form, I have 2 to the 10th. Well, I know that's going to be 2. Let's see, what adds up to 10? 2 and 8. So I know that 2 squared times 2 to the 8th would add up to be 10. So I know that that one works. Are there any 2 numbers that multiply to 10? Yeah, 2 and 5. So I can do 2 squared to the 5th power, and the 2 and the 5 would multiply to be 10. It then wants us to find a third equivalent. I could do this with subtraction even, right? What's a number that minus another number is 10? Well, how about 12 and 2? So I could do 2 to the 12 divided by 2 squared, and that would also be the same thing. Okay, so you can do these as much as possible, multiplying, dividing, etc. So let's try this next one. So 3 to the 7th, sure. What are two numbers that add to 7? 2 and 5. So this could be 3 squared times 3 to the 5th. Now this one doesn't really multiply anywhere, so that one's probably not going to work for me. But I can find, I could probably do it, how can I do it another way? How can I do it another way? Oh, how about, is there a number that's when divided by something is 7? Yeah, 14 and 2. So if I had 3 to the 14th to the 1/2, haha, because 14 times 1/2 would be 7. So that one would work as well. And finally, I'll do my division one. So let's just say 3 to the 10th divided by, what do I have to divide that by for it to be 7? Well, it's like, what number will I have to subtract from 10 for it to be 7? That would have to be 3. There we go. And so that's essentially what it's asking you guys to do on this one. So good luck with that. Fight through that one. Set. So now it wants us to determine whether all three of the expressions in each problem below are equivalent, and it wants us to justify why this may be true. To do this, we can do a couple things. We could look at it in terms of what our base values are. That's kind of the best way to do this. So we have 5 times 3 to the x minus 1, and then 15 times 3 to the x minus 2. So look at what happens here if we look at 15. 15 would be, we could rewrite 15 as 5 times 3, right? Because 5 times 3 is 15. And then this is being multiplied by 3 to the x minus 2. Now, we have two base 3's here. This one is to that invisible first power, right? There's that invisible first power there. And so what we know is that when we multiply things with the same base, we add the exponents. So 3 to the first times 3 to the x minus 2 is going to be the same as if we add these circled portions together. So it would be 3 to the 1 plus x minus 2. And when we simplify 1 plus x minus 2, we get 3 to the x minus 1, because 1 plus a negative 2 is a negative 1. So this whole bit turns into 3x minus 1. So this becomes 5 times 3x minus 1, which just so happens to be the same as this. Great, so we've justified those two. What about this third one? Oh my gosh, what do we do here? So when I look at this, I have this fraction, the 5/3. What do I do about that 5/3? Well, remember, whenever we're doing anything to a negative power, it puts it in the denominator. So 5/3 is the same as 5 times 3 to the negative 1, right? Because we know, I don't know why this scan's doing anything. Go away. No one cares. 5 times 3 to the negative 1, right? Because anything to the negative 1 power, if I had x to the negative 1 power, that's the same as 1 over x. It's the inverse, as we typically call it. So that this is already in the denominator. So if I had 2/3, that's going to be the same as 2 times 3 to the negative 1. And here I have 5/3, so that's 5 times 3 to the negative 1. So I just rewrote that circled portion, and all of that is being multiplied times 3 to the x. Well, now that I have the same base, we get to go back to those rules. And remember, when we have the same base multiplied by each other, we add the exponents. So this becomes the same base, and then negative 1 plus x. Now, if I were to rearrange negative 1 plus x, I have 3 to the x minus 1. So I have, this all becomes 3 to the x minus 1, leaving me with 5 times 3 to the, to the x minus 1. And so sure enough, They are all the same. Okay. Let's see if we can do this again. So now we have 64, 2 to the negative x, 64 over 2 to the x, and 64 to the 1/2 x. So this one's actually pretty cool. We can see how this works. So this one, I just hate negative exponents, right? Negative exponents are so hard to work with, so let's just get rid of it. But we know that whenever we have anything to the negative exponent, we just put it down. So here we have 2 to the negative x, so that just means this goes in our denominator, and we get rid of that negative. So that's the same as 64 over 2 to the x power. Cool. Got there. All right. 64 over 2. Oh, it's the same thing. All right. We've proven these are the same thing. That's neat. But what about this one? 64 times 1/2 to the x power. Well, whenever we're raising a fraction to an exponent like this is actually 64 times 1 to the x, 2 to the x, because it's going to be multiplying by itself x times. Now, here's the cool thing. 1 to the x power is always going to be 1. No matter what number we plug in for x, it's always 1. 1 to the x is 1, because 1 squared, 1 cubed, 1/3, 1 to the millionth, it's always 1 times 1 times 1 times 1, which is always 1. So this just becomes 1, and so what we end up with is 64 times 1, 2 to the x. Well, if we just combine our fractions, 64 times 1 is 64, 1 times 2 to the x is 2 to the x. We get 64, 2 to the x, 64, 2 to the x, 64, 2 to the x. So yeah, these are all equivalent to, and we've shown it. That's the other thing. We have to justify. And justify just simply means show your work. All right. So these ones get a little tricky, especially if you're not as familiar with our exponent rules. That's why on the inside of the homework sheet I included some of those. All right, let's go ahead and go to the next section using those rules of exponents. So it wants us to simplify each expression, and our answer should still be an exponential form. Exponential form means we need to have a base to some power, okay, a base to the power. So 7 times 7 times 7, that's our base. 3, 5, 2, whenever we multiply across the same base, we add our exponents. So 3 plus 5 is 8, plus 2 is 10. So this is 7 to the 10. 3 to the 4th to the 5th. Whenever we're raising an exponent to another exponent, we multiply our exponents. So this is 4 times 5, so this is 3 to the 20th. All right, this one gets a little tricky. 5 to the 3rd to the 4th. Okay, so we're going to multiply there, so that's going to be 5 to the 12th times 5 to the 7th, and now we add our exponents, 5 to the 19th. Okay, x to the 3rd, x to the 5th, we add our exponents, x to the 8th. X to the negative b, those negatives. So that tells us to invert it, so let me rewrite this, 1 over x to the b, right? We inverted it, we put it down there. X to the a times x to the b. So we don't have numbers here, but we know we add those together, so it's x to the a plus b. X to the a to the b, so we know we multiply those together, so that's the same as x to the a times b, ab. Y to the a over y to the b, so we know we subtract when we divide, so this is y to the a minus b. Ooh, this one's fun. Y to the a to the c all over y to the b. A to the c means we multiply, so that's y to the ac over y to the b, but now we subtract, so this is y to the ac minus b. So these are how all our rules work. Remember, when we're multiplying across, we add these together. When we're raising to the power, we multiply. When we're dividing like this, we subtract. So keep your eyes open for that. I'll let you guys do these more complicated ones on your own. But be sure you're adding, subtracting, multiplying. Those are mostly the things that we're going to be doing. And that's going to be your homework for tonight. It's challenging, especially depending on your comfort level. It's challenging to know exactly what all of these rules are, because there are a lot of rules. Make sure you look at this page on the inside of your front packet because it talks about a lot of what those rules are. For example, here's the inverse rule. That's going to be incredibly important. And then also getting more comfortable with our radicals so that we know how that works. All right, team. Good luck, and let's get to it.